Hey everyone, my name is Imal and welcome to a series of videos where we will be implementing linear regression from scratch. This is the second video of the series of videos on linear regression from scratch. Let's jump right into it. We'll start estimating the likelihood of parameter theta. Because this is what we essentially want to do. Find theta so that we can predict y for unknown values of x. Like I'll keep repeating this. We want to find theta so that we can predict y for unknown values of x. The likelihood of theta given x comma y can be modeled using the PDF, which is the probability distribution function of a normal distribution and this is how we are going to go about solving for likelihood of parameter theta. So on the left hand side of the equation you would see likelihood L, likelihood of theta given x comma y is equal to probability of getting x comma y given theta. Let me repeat that again. Likelihood of getting theta given x comma y is equal to probability of x comma y given theta. Let that register in your head, right? So what I'm saying is if my likelihood of getting theta given a certain x comma y is something, that is essentially equal to the probability of getting x comma y from a certain theta. And this can be represented as products of values ranging from I equal to 1 to n. And that's what you see in the next line is equal to values of I ranging to n product of probability of xi comma yi given a parameter theta. And in the third line, in the final line of the equation, it's a product of I ranging from 1 to n, 1 divided by square root of 2 pi sigma e to the power of minus of yi minus xi theta xi transpose theta square whole square divided by 2 sigma square. Now this equation, you may ask, where is this equation coming from? This equation is coming from the probability distribution function of a normal distribution, where we've replaced values for mu and sigma. Mathematical intuition will now look at log likelihood expression. So since we are interested in theta, we can treat the other variables as constants and put everything under a constant c. And since dealing with exponents can be tricky, let us take a log to get rid of the exponential and work with sums instead of products. So now the new log likelihood expression is. So what we are essentially doing is we had a likelihood expression which was in terms of exponentials, e to the power something. We don't want to work with exponentials, and we also know that there are a lot of constants with respect to theta in our equation. So what we're doing is getting those constants not out of the equation, but putting them in under one constant c, and removing the exponent by taking a log on both sides. And then now we say that we are looking at the log likelihood. Instead of looking at likelihood, we are looking at the log likelihood expression. And this is what it is. Log likelihood expression is L of theta given x comma y. And you would see a small l here when compared to the previous L. So L of getting theta, the log likelihood of theta given x comma y is equal to log of capital L theta given x comma y, which we saw earlier in the previous slide. So now we're taking logarithm of this equation, and like I said, we are going to combine all constant terms and put it under c. If you go to the previous equation, if you just go a little bit behind in this video, you would see that it has 1 divided by square root of 2 pi sigma times something. So 1 divided by square root of 2 pi, all of that would come under c here. And other things, because all of those are not dependent on theta. So we are treating them as a constant c. C minus sigma of I ranging from 1 to n minus of yi minus xi transpose theta the whole square. just read through this equation once again. And then you will try, I want you to read through this and digest this. So what we did, we took out the exponentials by taking a logarithm. And log e to base e is 1. So whatever was in the power has come down now to be a normal multiple. Okay? The new log likelihood expression is L of theta given x comma y is equal to c minus norm of y minus x theta the whole square. And what do you mean by norm here? It's essentially the magnitude. All right? So now we have a very simplified representation to find the log likelihood expression. Remember, where did we start? We started off with the likelihood expression. And even before the likelihood expression, we started defining the probability of getting x comma y given theta. We also defined the likelihood of getting theta given x comma y. And then we came further and derived this log likelihood expression. So now we have the log likelihood expression of theta given x comma y. But we are yet to find an expression for finding theta given x comma y. We'll do that now based on the following. So we're going to make some assumptions. We're going to say that since log is a monotonically increasing function, which is always increasing, never remaining constant or decreasing, maximizing L is same as maximizing capital L. Okay? So what we're doing is log is always increasing and it will not decrease or it will not remain constant. So what we're saying is if I'm looking to maximize capital L, which is my likelihood estimate, I'm essentially looking to maximize small l as well, because small l is always increasing. So we are saying there's no difference between maximizing capital L or small l, because log is monotonically increasing, and if I'm tracking only log likelihood, I'm essentially also tracking likelihood. Second point, the constant c has no effect on the location of the maximum, which is also true because we talked about c having no effect on theta. And thirdly, we remove the minus sign that we saw in the previous equation and consider the problem as a minimization problem instead. So this allows us to model the problem as a minimization problem instead of maximization problem by removing the minus. We're just changing the direction of the way we wanted to solve a problem now. So we are going to use these three things. We're going to base our further analysis or we're going to go further into the video based on these 3 points. Therefore now our maximum likelihood estimate for theta given a data set x comma y simply becomes theta is given by argument of theta norm of y minus x theta the whole square. And this is what we saw earlier in the important formula. This is the second important formula that we wanted to reach and we've reached. Okay. Now we're moving on to some more interesting stuff. We've now found what we need to do to get the maximum likelihood estimate of theta with a given data set x comma y. Now let us represent our minimization equation as follows. J of theta is equal to norm of y minus x theta square. Okay, so this is the minimization equation now. So we got this equation in the previous slide. So this equation is also known as the cost function or the loss function. And this is the equation we intend to minimize. And this is a very important result. This is the equation this is the third formula that we saw in the first slide. And as a result of minimizing this equation, we will be able to find the best parameters. That's what it says, right? This is what we want. We've been trying to find theta. We've been trying to find the maximum likelihood of theta given x comma y. And we've been seeing how can we do that. And we started off with finding the maximum likelihood And then we went to the log likelihood, and then we've reached to the loss function here. And now, if we minimize this loss function, we will get what we want, which is the parameters theta, which is the best estimate for parameters theta given the data set x comma y. All right? How are we going to minimize this equation? That is now our focus for the rest of the video. We've reached a stage where we have a minimization equation. How do I minimize this?